Right, so our last section for this week is section 5.6 in your packet, or if you're looking in your book, it's still section 8.5, and it's on vectors in 3D. Okay. One thing that's nice about 3D vectors is we're going to really do a good overview of everything we did in 2D. We're going to extend everything to 3D, and the only thing that's going to be new is what's called a cross product. So everything else is going to review 2D. All right, so here's what your X, Y, and Z axis look like in 3D. Okay, and this is called a right-handed coordinate system, or it follows what's called the right-hand rule, okay, which is in your book on page 354. Okay, it says basically if your index finger points in the positive x-axis, your middle finger points in the direction of the positive y, then your thumb will point in the direction of z. All right? So, point your index finger. It's hard to do on this one, but positive x, middle finger, positive y, z, in this case is going up. Okay? So, this area down here, this is what you were working in before. Okay, this is your XY plane, right? Now we're coming up off of the plane, and we're going to use our z-axis. All right. As far as sketching, we won't be doing the sketches in 3D. We did it in 2D a lot, but 3D it's a lot harder to sketch. So everything we really do is going to be numeric, less visual. All right. So in 2D. Okay, that's our formula for finding the distance between 2 points in 2D. Right? It's the distance formula. Right. In 3D, okay, our points have an x value, a y value, and now a z value. So you can still call these coordinates, or you can call them ordered triples. Okay, ordered pair is for 2D, ordered triple is for 3D. Okay. Does anybody have a guess what the distance formula is going to be in 3D, or maybe just explain how it's going to change from 2D? What do you think you're going to add on to it? Brian?
I feel like it's going to be the same thing, except you add on underneath the square root, you're going to do a plus z, parentheses z2 minus z1 and parentheses squared.
Yeah. And that's pretty much how every formula is going to work to extend it to 3D. Just add something on to the end of it. Okay, in this case, the difference in the x is squared, plus the difference in the y squared, plus the difference in the z squared. Right, and the first problem we'll just find the distance between those 2 points. Right, so since this is P1, we'll let P1 be the x1, y1, z1, and then P2, the x2, y2, z2. All right. So can someone tell me what I'm going to subtract first in parentheses? 4 minus negative 1. Yep. Okay, plus, all right, what comes next?
Negative 2 minus 3.
Yep, negative 2 minus 3. Plus, what's my last one?
5 minus 2.
5 minus 2. Okay, now we just have to do that out and see what we get. As always, if you get a nice answer that can be reduced, let's make sure we do that. All right, so we're going to get 4 minus negative 1 is 5 squared. Negative 2 minus 3 is negative 5 squared. And 5 minus 2 is 3 squared. So what do I get there?
59.
Square root of 59. And 59, if you try to reduce that, I don't think we can reduce it. Okay. Any questions on that? All right, so that's distance in 3D. All right. Now we're going to start to talk about vectors in 3D. Okay, in 2D, if we were going to write a unit vector, we had the unit vector I, which was the unit vector that pointed in the horizontal direction. J was the unit vector that pointed in the y-axis direction. But now we're going to need one more unit vector. Okay? We're going to use K. Okay? So I is the unit vector on the x-axis. J is the unit vector on the y-axis. K is the unit vector on the z-axis. Okay? And what we say is that vectors I, J, and K span, S-P-A-N, they span 3D space. Meaning, if you pick a location anywhere in 3D space, I can stack I, J's, and K's together to get to your point. Okay? Now, I, J, and K are point in the positive direction on each axis, but if we had to go in the negative direction, what would we do to them?
Negative.
Yeah, just make them negative. Okay? Make one of them negative, and then you're in the negative direction. If you're going to write it in the algebraic form, it would be A comma B comma C. Okay, and remember, those are called the components. Okay, A would be the x-axis component, B the y-axis, C the z-axis. Okay, you already have this from 2D, okay, but I'm mentioning it again because it's also true in 3D. If you draw a vector that starts with its initial point at the origin, it's a position vector. Okay? Same thing we had in 2D. Right. So in 2D, this is how you found a position vector. Okay? Again, you already have that formula from probably Monday. And where are these coming from? These are the coordinates of the initial point and terminal point. Okay. What about in 3D? What do you think, or how do you think I'm going to represent my initial point? Let's just start with just the coordinate itself, and then we'll do the position vector formula. So what's my initial point going to be? X1, Y1, Z1. Yep. And the terminal point, x2, y2, z2. All right? So now, to find the position vector, what am I going to add onto the end of this formula? Yeah, we're just going to add z2 minus z1. Right, so really, if you write down the formulas on your reference sheet for 3D, you could just use those formulas, and then if it's only a 2D problem, just block the z part. Just pretend like the z part is 0. Okay? All right, so let's find the position vector between these 2 points. P1 is my initial. P2 is my terminal. Okay, we'll write it. Let's write it in the algebraic form, and then we'll also write it with ijk after. Okay, so the first one is going to be what minus what? 4 minus negative 1, which is 5. Next part? 6 minus 2 is 4. 2 minus 3 is negative 1. Okay, or how about if you wrote it with ijk? So make sure you're comfortable with either notation. Okay. Questions on position vector? All right. So next thing we're going to look at is some formulas for adding, subtracting, multiplying, or scaling, and finding the magnitude. Okay. We had all of these same formulas in 2D. In 2D, if you want to add vectors, combine the x components and combine the y components. Well, now we just have one more component to combine. We have to combine the z's. If you're adding, then you add the x's, you add the y's, and you add the z's. If you're subtracting, then you subtract the x's, subtract the y's, subtract the z's. Okay, and just use the same formula.
So should that be like v plus or minus w plus or minus? Never mind.
Right. How about a scalar? Does anybody remember what property I said having a number on the outside of the vector is kind of like? Yeah, it's like distributive. Okay. So before, we had to distribute the scalar to the x component, to the y component. Now we have to distribute it as well to the z component. Okay, so just one more component to multiply it by. Okay, and for the magnitude of a vector, that was your formula in 2D. Square the x component, square the y component, add them up, and take the square root. What else am I going to put on this as plus z1 squared? Right, so to find the magnitude of a vector, square each component separately, add them all up, and then take the square root. Okay. Any questions on those formulas? Yeah?
What formulas are different between 3D and 2D?
The only thing that's really different is what we're going to do called a cross product. Cross product does not exist in 2D.
Okay.
It's impossible to do, and you'll see why.
All the formulas we learned in the past couple days we can use in 3D?
Yeah, it's just a very small extension.
Okay.
Mhm. All right, let's, I'm not going to go through each one of them, but let's try to do v plus w. All right, so it would be 5i. And then what's the next part? Minus j. Plus 3k. Just think of it as combining like terms. The i's, the j's, and the k's. You could also write in the angle brackets 5, -1, 3. Comma between them. All right, how about magnitude? Okay, can you explain how you got that, Brian?
It would be, since within the x1 is 2, it would be 4.
So 2 squared gives me 4, yep.
And then plus 9, because 3 squared is 9.
Okay,
And plus 4 here, which is the -2 squared.
-2 squared. Okay, so we get 4 plus 9 gives me 13, plus 4 more gives me 17. So we get the square root of 17. All right, and I guess we can do a scalar product. Let's triple w.
9 minus 12j
Plus
plus
15k.
15k.
Yep, just multiply everything by 3. So we say 9i minus 12j. What's the last one?
Plus
15k. 4, 9, -12, 15. Okay. Any questions on that? Okay, dot product. Right, so dot product in 3D, it's pretty much the same as 2D. If you want to find a 3D dot product, you multiply your x components, multiply your y components, and then multiply your z components. You're going to take each one of those answers and then add them up. Right, so when you do this out, what kind of answer are you going to get for the dot product? What kind of quantity will it be?
Scalar.
A what?
Scalar.
A number, yeah, it's just a number. Okay, it's not a vector. Okay, it's like a scalar, it's just a number. All right, let's try a dot product. Okay, so vector v is 2i minus 3j plus 6k, and w 5i plus 3j minus k. And we'll write it out like what times what plus what times what. Okay. So Jacob, what are the first two things I would multiply together?
2 and 5.
2 times 5. Leon, the next two?
-3, 3.
-3 and 3. And Matt, the last two?
6, -1.
6 and -1. Okay, let me just do that out. So we're going to get 10 minus 9 minus 6. Yep, so 10 minus 9 gives me 1. And 1 minus 6 is negative 5. Okay, now once we have the dot product, what does that allow us to do? Yeah, it helps us to find the angle between two vectors. Okay, what was our formula to find the angle in 2D? So the dot product over the product of the magnitudes equals cosine theta. Well, it's exactly the same formula. The only difference is it's a 3D dot product divided by a 3D magnitude times a 3D magnitude. But the formula itself stays the same. It's just the things you plug into it now are 3D, not 2D. Or they come from 3D vectors. All right, so I think these are the same vectors I just had up above. 2i minus 3j plus 6k. And 5i plus 3j minus k. Yep. So we already know the dot product. Yep. That's what we just did up above. Okay, and now we need the magnitude of u and the magnitude of v. Okay, so just tell me the three numbers we're going to add and how we get those numbers.
4.
Yep. How do we get the 4? You square the 2. What about the 9? It's the negative 3 squared and the 6 squared. Square root of 49, which is 7. Okay, so the length of u is 7. How about, let's find the magnitude of v.
Square root of 25 plus 9.
So 5 squared plus 3 squared plus 1. Square root of 35. And how do I set up my equation now to find the angle?
Cosine theta equals negative 5.
Negative 5 over 7 squared 35.
7 square root 35. Good. Right, and to get theta by itself, take the inverse cosine of what's on the left and what's on the right. And you can do it in degrees or radians. I'm going to do this one in degrees. Just follow the directions, whatever the problem says. Negative 5, and you have to be careful here. How do I type this in?
Yeah, the parentheses.
Parentheses. If I don't, it's going to do negative 5 divided by 7 first, and then it multiplies by square root 35. Okay, so if you want to type it in all at once, do it just like this. And the angle is 96.93. Okay, and that's the angle between the two vectors. Now, in 3D, there's all kinds of angles you can find. You could find, for example, if you had just a single vector, you could find the angle that it makes with the x-axis, the angle with the y-axis, or the z-axis. Okay, you could find all those angles separate. In 2D, if you just had a single vector, there's really not that many things you can find. You could find the angle with the x-axis, or you could find the angle with the y-axis. There is no z-axis. All right? But this is the angle that two vectors are making with each other, okay? Not with an axis. All right, so let's take a look at the cross product. Okay, the cross product is actually section 5.7. You have the very first page of it, but you don't have anything else on cross product. Right? So you're really going to need the notes for this. And I'm not doing the cross product the way they explain it. All right, so what is the cross product? Okay, basically, it's a second way to multiply vectors together. All right, so because of this, we don't want to say something like, I want you to do v times w. That's vague. Do you mean v times w with a dot product or v times w with a cross product? Yeah, you pronounce it v cross w. Now the reason it becomes important is because now we're in 3D. In 3D, you can do cross product. If you're only in 2D, then it's not really an issue. You don't have cross product. Okay, and there's different applications, and we'll see based on the result of the cross product what some of the applications might be. All right. So we'll practice kind of the numeric kind of approach. How do you calculate it? And then we'll see, well, what does it really mean, the answer we're getting. Okay, the way we're going to do a cross product, okay, there's many ways to do it, but we're going to use what's called Ceris's rule. Okay, so Ceris's rule is basically a way to set up the problem using a matrix style to do it. All right, so these would be our two vectors. Okay, all the a, b's, and c's would be numbers. For now, we'll just leave them generic. Okay, and to use Ceris's rule, the first thing we have to do is set up a 3x3 matrix. Okay, and in that matrix, in the first row, you're just going to put I, j, and k. Okay, in the second row, you're going to put the coefficients of v, a1, b1, c1. And in the third row, put the coefficients of w, a2, b2, c2. And you do want to make sure that we do them in the order they're listed. Okay, so what we're finding here is v cross w. We're not doing w cross v. We'll look at that after and see what happens. Okay, so v, row 2, w, row 3. Okay. Does everybody have up to that matrix? All right, so next, what we're going to do is copy down the first two columns, column I and column j, to the right of column k. So we're going to add two more columns onto the end. We're going to put a copy of the first column on the right and a copy of the second column to the right of that. Okay, so I still have the original, I, j, and column k. But now I'm going to put a copy of column I to the right, I, A1, A2. And then to the right of that, I'm going to put a copy of the second column, J, B1, B2. Okay, so at this point, don't worry about anything that's circled here. You should just have 5 columns. Okay, any question up to that step? Okay. And now we're going to look at the diagonals. Okay, there's really 6 different diagonals we can look at here. And the diagonal has to include three things each. Okay? 2 of them are going to be numbers. 1 of them is always a letter. Okay? There's diagonals that, if you wanted to think of them as like slopes, some of them are slanting up, positive, and some of them are slanting down, like a negative. Okay? And the calculation we have to do is right here. You take, and I'm just going to call it red 1, red 2, red 3, blue 1, blue 2, blue 3. Right? So we have to take the product red 1, product of red 2, the product of red 3, and add them all up. And then we have to subtract the product of blue 1, subtract the product of blue 2, subtract the product of blue 3. So it's not too hard. We just have to remember what's what. Mhm.
How exactly will we write that down in our notes?
Just do 1, 2, 3, 4, 5, 6.
Yeah, if you didn't have a different color, you could just call them diagonals 1, 2, 3, 4, 5, 6, if that's helpful. Do you want me to erase it and do it that way? No? Okay. Or if you have a pen and a pencil, use your pen for one of the diagonals, use your pencil for the other. Blue pen, black pen, something like that. And before we start, does anybody have an idea yet of the type of answer you think we're going to get here, like the quantity? What do you think it's going to be?
It's gonna be IJK.
It's going to have ij's and k's in it?
Yes, it's gonna be IJK.
So if it has ij's and k's in it, what would it be?
Okay.
It would be a vector. Okay? So the cross product of two vectors is a vector. And it's a special vector. Okay? It has a connection to the two vectors you're crossing. We're going to see what that connection is after we find a cross product. Okay. Does everybody have the formula? Okay, I can come back to it too as we're doing a problem. We'll come back and reference our diagram. All right, so let's find the cross product between these two vectors. First time I'm going to do v cross w. After I'm going to do w cross v. All right, what goes in the first row?
IJK.
I, j, k. And then in the second row? 2, 3, 5. 1, 2, 3. Okay. Then what do I do after I've created my 3 by 3 matrix?
IGA, put X and K.
Yep, put a copy of I and j to the right of it. So I, 2, 1, j, 3, 2. All right, now I'll circle my diagonals. Okay, and I'll use the same pattern I did on this page. So I'm going to circle all the ones that go down into the right in red, and I should have 3 of them. There's 1, 2, 3. Okay, I'm going to circle the diagonals that go down and to the left in blue. And there should be 3 of those. 1, 2, 3. Now, the rule, if you're following Ceris rule, is to take the product of all the red diagonals, the ones that slant down into the right. Okay, so let's find all those products and add them up. What's I times 3 times 3? So we get 9i. J times 5 times 1? 5j. And k, 2, 2. 4k. And now you subtract all the blue diagonals. Okay, what's 1, 3 in k? Minus 2k. 2, 5 and I? Minus 10i. And the last one?
Minus 6K.
3 times 2 is 6j. All right. Now what can I do with that?
Do you include negatives when you do this?
Yes. Yep.
So like you say it was in V, it was 2i minus 3j, you put all the negative 3's.
Yep. You got to include the negative, so you got to be careful. If you're subtracting a negative in that second part, it would turn positive. Mm-hmm. All right. So now combine your like terms. What's our I component? Negative I. Our j component?
Minus j.
You got a 5 minus 6, and And our k component?
Plus K.
Plus k. Right, so this one just came out with coefficients all 1 and -1. Doesn't have to happen. But that's v cross w. All right, let's find w cross v. Okay, what's going to be different about w cross v in the setup? What's going to happen?
The 1, 2, 3 is going to be the second row rather than the third.
Yeah, we're just going to switch these two rows. So we're going to have 1, 2, 3, 1, 2. And 2, 3, 5, 2, 3. Okay, you don't have to circle your diagonals if you can just see it. So this time let's just do them. What's I times 2 times 5? 10i. J 3 2. 6j. K 1 3. It's 3k. Now go the other way and subtract. K 2 2.
Minus 4K.
I 3 3.
Minus 9i.
Minus 9i. And J 1 5.
Minus 5K.
Minus 5j. Okay, what's my I component here?
Just I.
Positive I,
K.
positive j,
Negative K.
negative k. Yeah. So what's different about these vectors if you were to sketch them?
They're opposites.
Which means what?
The,
Going opposite direction.
yes.
They point in opposite directions. They have exactly the same magnitude, but they point in opposite directions. So this might be one of the first times you've ever done multiplication, and switching the order does not give you the same answer. It gives you the opposite. So what does that mean about vector cross product multiplication? It's not commutative. Okay, the commutative property does not work.
Isn't
It's what?
inverse? Like they're inverses when you flip it.
Well, the answers are opposites. Yeah, opposite directions. One is like multiplied by like a -1. All right, so now I'm going to take one of these vectors and let's find the angle between, let's say, v cross w and which one do we want to do first? Let's do both. Let's find the angle. Let's find the angle between our cross product and vector w and our cross product in vector v. All right. Now, first of all, I want to know why I can write this. Why this makes sense.
Because the parentheses.
All right. So I have my parentheses. Why does this make sense thinking in terms of quantities? Yeah? They're both vectors. You can only find the dot product of a vector and a vector. V cross W is a vector. W is a vector. What is the answer to this going to be? It's going to be a number. Okay? The reason I'm finding the dot product is because that's one step in finding the angle. Okay, so let's find the dot product. And then we'll find the magnitude of V cross W and the magnitude of W. All right, so V cross W is, let's write it like this. -1, -1, 1, dotted with W. 1, 2, 3. So yeah, -1, -2, plus 3. So what's the dot product?
0. W is the
Dot product is 0. So if we want to know the angle, we don't have to go any farther.
It's 90.
It's 90 degrees. It's orthogonal. Okay, so the vector we just found with the cross product happens to be orthogonal to W. Well, let's check it the other way.
It's the same thing. It's
Yeah, it's going to come out the same thing. If we did W cross V, I'll just put it here. If you have room on your paper, actually, no, stick with V cross W, sorry. Except we're going to dot it with V. Right, so V cross W is negative, yep, -1, -1, 1. And what was V? 2, 3, 5. So you're going to get -2 plus -3 plus 5, which is 0. So that means our cross product is orthogonal to V, and it's orthogonal to W.
I mean that V and W are parallel.
It doesn't mean V and W are parallel. No. In fact, they're not. They're not parallel. A quick way to tell if they're parallel, if one vector is a multiple of the other, like if this was, each one of these was doubled, like 2, 4, 6. Look, if you look for that pattern, you can tell if vectors are parallel that way. So these aren't parallel, but what we did discover is that the vector created from the cross product is orthogonal to both of the original vectors. Right? So something like that you could use. You could use in like a simulation or build it into like a computer gyroscope. If you have two vectors, say that represent vectors in a horizontal plane, and you find the cross product, it would tell you which way is up. It would also tell you which way is down if you did it the other way. All right. So it could help, I would think, in some kind of navigation situation for a computer. As long as you had two vectors in the horizontal plane, the computer could figure out which way is up and which way is down, just by using a cross product. All right, so we didn't really get into cross product that deep. In a calculus class, you'd probably look at, well, what is Ceris's rule and why does it really work? Okay? You'd have to kind of get into the proof of Ceris's rule and the explanation. We're just looking at the mathematics here. Okay. Great. Any questions on finding a cross product? All right. So got the angle. Did that. I'm not going to go through the problem, but one use for a cross product would be in a problem like this. Let's say you had a lever, and there was a rod going through that lever. Okay? As you pull on this lever, what happens to this rod? It rotates. Right? So as I pull on the lever, the rod is rotating. So basically what's happening is my lever is at a 90-degree angle to my rod, and I could use a cross product to figure out the torque. Okay? What's interesting about, kind of different about this problem and why it gets into calculus is because the torque is constantly changing. Okay? If my rod is almost, let's say my rod was straight up, and I pulled down on it, is it going to rotate at all? No. That rod that's connected? No, there's no horizontal component if I just push down. But as I start to turn it, then I push down, it will rotate. So the torque would be its greatest in the horizontal position. Okay, that's when you get the most torque. As you start to approach vertical, you're not getting as much torque on it. So there actually, the way I made it a pre-calculus question is to say, let's pretend that you're at an angle of 60 degrees. Find the torque at that exact moment. Versus in calculus, it would say, pretend that the angle is a variable, come up with an expression to find the torque for any angle, because the torque is constantly changing. All right. So that's an application of a cross product. And you might do that problem next year in calculus. It's actually from Mr. Babb's text. Well, the text he uses. Right. And of course, the length of the rod makes a difference too. Okay, you might have seen, like, if you can't get, like if you're working on your car and you can't get a tire off and you just have like a 1 foot breaker bar, maybe you put a pipe on it and make it 2 feet long, and then you get a lot of torque. You also risk breaking things, but that's how you can get more torque, make your lever longer. All right. Okay, so the homework, most of it's in the packet, but I had to make up one question that's not. Page 363. Okay, try 15, 17, 29 to 35 odd. 41, 43, and 51. And lastly, find the cross product between vectors v and w. And I'd like you to do the cross product both ways. Since we already know the relationship between switching the order, once you find the first cross product, the second one is pretty easy to find. Okay, so tomorrow we'll go over any questions on the homework. Okay, we have our test on vectors, and that will finish chapter 8. Okay, so next time we come in, we'll be starting chapter 9.